So lots of pretty pictures today because many of the pretty pictures that you see in astronomy are in fact pictures of the interstellar medium. Yeah, I guess it's a big related situation here. So let's full screen it here. So the interstellar medium is the stuff between the stars, gas and dust between the stars. And now it's washing it out. We can't have that. So let's just get mood lighting for the house lights here. That's not very moody at all. Where's the slider? Yep. Okay. What's that? Show details. Oh, thank you. Thank you. Because this is so bright out, I'll stop complaining about this, but why it's so much better than before when I could just touch a physical color instead of having to go through a panel and all that sort of thing. There, you see a little better. So, interstellar medium, the stuff between the stars, gas and dust between the stars. We, as you probably know, live in the Milky Way galaxy, which is one galaxy out of hundreds of billions of galaxies within the observable part of the universe. The fact that it's 100,000 or so light years across in its disk, and that we do not have interstellar travel capabilities right now, and that even if we did, we'd sure have to wait a long time to get the pictures back, means we don't have any photographs of our galaxy from the outside. We're inside our galaxy, so we have to infer what it looks like from the inside. Well, we've done that, and so we can show examples of galaxies which probably look fairly similar to the Milky Way, what it would look like if you could only see it from the outside. Here's one, NGC 6744, probably looks pretty similar to what our galaxy looks like as seen from the outside. NGC, as in the new general catalog, object number 6744, in the new general catalog, which was indeed new when it was published in 1885. But we still call it the new general catalog, NGC. Many deep space objects have NGC designations. A smaller subset, a little more than 100, have M designations. This is the spiral galaxy M83. It's got an NGC number as well, but because it's on a special M list, Messier's list, Charles Messier's list, who was a French amateur astronomer / rich dude who had a passion for finding comets. Some of you have heard this story before. He had this passion for finding comets. Deep space objects like galaxies and nebulae and so forth look like fuzzballs visually through a telescope, even a very large one, because our eyes aren't able to take time exposures. Comets also look like fuzzballs, especially when you're first discovering them. So what would happen to Messier is he kept finding fuzzballs that he thought might be comets, and then he goes back and sees that no, they're not moving amongst the stars, so he's not seeing motion due to the orbit of the comet around the sun combined with Earth's orbit around the sun. It's in the same place. Why? That's not a comet. So he made a list of things that are not comets, fuzzballs that he was seeing, so that he wouldn't keep getting excited for nothing when he saw them again. And so he numbered them. And so M83 is number 83 on Charles Messier's list of things that are not comets. Well, this is spectacularly not a comet. It's an entire galaxy of stars, although Messier wouldn't have known that at the time. And it's just one of history's, to me, very amusing ironies that Charles Messier is much more famous for his list of things that are not comets than he is for any comets that he discovered, which was his actual passion. So I do like to, when I'm talking about M objects, why here's number 83 on Charles Messier's list of things that are not comets. The galaxy M83, it's a spiral galaxy like our own Milky Way galaxy. It's called a spiral galaxy because of the pinwheel-like appearance. And along the arms of the spiral, you can see some distinct features here. You see these lovely pink clouds, and those are what are known as H2 regions, where H2 means ionized hydrogen. And those are, y'all remember when I had a hydrogen lamp and I turned it on and it glows a lovely pink color? The physics is essentially the same. Those are regions which are filled with ionized hydrogen, electrons recombining with bare protons, and dropping down the energy ladder rung. Those which, on the way towards the ground state, drop from a higher level to n equals 2, why they produce the visible spectral lines of hydrogen, also known as the Balmer lines, right? So n equals 3 to n equals 2 is the Balmer alpha line, and it is a lovely, do you remember what color is the Balmer alpha line? N equals 3 to n equals 2 transition. Not that one, you're a little too high there, not that one. This is the lowest energy Balmer transition. So of the visible lines, it will be the one with the longest wavelength. So that's the lovely red one. 4 to 2 is a shorter wavelength. Why, that one would be teal. You're supposed to say it now, yes. Yeah, that's the lovely teal or aquamarine or whatever you want to call it. And then there's 5 to 2 and 6 to 2 that are also the visible part of the spectrum, which you might even call indigo even, right, and bluish purple or whatever. Those 4 visible lines combine to make a pinkish color, either when I turn on a hydrogen lamp to let you see that, or when you have a whole giant interstellar cloud where baby stars are being born, and gas is being ionized by ultraviolet light from hot O stars forming within a birthing star cluster. So those are stellar nurseries. The pink clouds are H2 regions. And you can also see these dark areas. Those aren't regions where there are no stars. Those are interstellar dust clouds, where dust is scattering light before the light from the stars behind it can reach us. Did you have a question?
Yes. Related but unrelated question. What does the WFC3 and UVIS mean?
Oh, all that business. Let's see. So WFC3 stands for, I think, Wide Field Camera 3. So it's the instrument on the Hubble Space Telescope, that took the picture. And UVIS, I think it's the ultraviolet and infrared spectrometer is what that stands for. Although you're not seeing a spectrum there, but I think that's what that stands for. You look it up and maybe I'm wrong, but I think that's right. And then this is a ground-based image from the European Southern Observatory with the miles per gallon. I don't know what MPG stands for. It's not actually miles per gallon. 2.2 meter telescope. And it uses Wi-Fi. I'm making that up too. Anyway, this is an optical photo from the ground, and then this is a zoom in with the Hubble Space Telescope to show more detail in there. So, do we see those sorts of things in our own galaxy? Why, of course we do. What constellation is this, as simulated by Stellarium? This is Orion. Yes, that's one of those constellations that everybody knows, even if they don't know constellations, right? Just like everybody knows Beethoven, even if they can only name 3 composers, they want Beethoven is on the list. I think Orion, the Big Dipper, which isn't actually a constellation, those are a pair that everybody knows about and can maybe even find, even if they don't really know any constellations. Let's see, you might have heard the terrible joke, which I've been sent multiple times now, where somebody says, they're rating Orion's belt, and they say, it's terrible, only 3 stars, a total waste of space. Anyway, Here's Betelgeuse, my second favorite star. What's my favorite star? The sun. Gotta give props to the thing that lets us live, right? Second favorite star is Betelgeuse because someday, we don't know when, it's gonna blow up good as a supernova. And when it does, you'll be able to see it in broad daylight. Total light will get comparable to like the full moon, so you read by the light of Betelgeuse when it blows up. Every time I see it, I'm like, blow up! Never does. Of course, in our frame of reference, if I'm ever going to see it blow up, it already done blowed up, and we're just waiting for the light to get here, because it's like 600 light years away or something like that. So, blew up in the Middle Ages. If it did blow up, then we're going to see it. Or maybe it hasn't blown up yet. In any case, about 10 times the mass of the sun, and it's destined to blow up as a supernova any time now, or any time now. It could be like, sometime in the next 100,000 years or whatever, right? So, anyway, so you're not likely to see it, but I'm rooting for it. But meanwhile, here we have the belt of Orion that you can readily see with the naked eye, even in light polluted Delaware. And the second star from the bottom sorry, I meant to say the sword of Orion. This is the belt. This is the sword of Orion. Betelgeuse, by the way, means shoulder of the giant, essentially. I sometimes see it as armpit of the giant, which I kind of like better. But in any case, here's the sword of Orion. Second star from the bottom, even to the naked eye, looks a little bit fuzzy. It looks maybe a little bit not quite star-like. That is enhanced if you look through binoculars, even more enhanced if you look through a telescope, because that is the famous, I forgot to put the picture, that's the famous Orion Nebula, as a matter of fact, which you've probably seen photos of before, which is the nearest H2 region to Earth, the nearest large H2 region to Earth. An H2 region, and this is something I certainly want you to know, so yeah, I guess I'll write it on the board, right, to emphasize that that's what this is. So, and I guess the audience at home should get to see what I'm writing on the board here. An H2 region is a stellar nursery where cute, giant baby stars are being born, because there's no such thing as a little baby star. I mean, if you want to consider the M dwarfs, the most abundant type, which are only about the diameter of Jupiter, as little, but I don't know, they don't generally consider Jupiter to be all that little either. So an H2 region is where cute, giant baby stars are being born. Oh, adorable. So H2 region, another name for that is emission nebula, because it's giving off its own light. And I think we've gone through, right, the Roman numeral designation for Roman numeral designation for ionic species in astronomy. Have we done that? We're not. Wow, you're looking at me like we probably, let's review it, shall we? Right. So we designate atomic species and ionic species in astronomy with the chemical symbol, followed by a Roman numeral, which, because we're astronomers, is one more than the number of electrons that have been removed. Why do we do that? One, we're astronomers. Two, there's no Roman numeral 0, and so therefore neutral hydrogen is called what in this designation? H1, H Roman numeral 1. Ionized hydrogen is H2. Is H3 a thing? No, it is not, because there's only one electron in hydrogen, so you can't remove more than one. So H3, not a thing. What would singly ionized helium be called? He2, right? He1 is neutral helium, He2 is ionized helium. Doubly ionized helium would be He3. He4 would be not a thing, right? Yeah, so that's the review of this nomenclature, right? Chemists, silly people that they are, would call that H+, just because it's got a positive charge on it. How stupid is that? So we'll stick with our Roman numeral notation. He said, how stupid is that? Secretly admitting that the chemical notation is probably better. Shh. Okay. In Mission Nebula, a stellar nursery. Aww. Where an open star cluster is being born. Come back millions of years from now, and there will be a star cluster where the Orion Nebula is now. UV light from the hottest O stars. Well, I guess from the O stars, and I think some B stars are hot enough for this too. It's mostly the O stars. Ionizes H in the surrounding nebula. So stars are born from clouds of gas and dust. And so as stars are being born, there's still hydrogen and other gas around them. Ultraviolet light from those stars ionizes H in the surrounding nebula, right, which is the Latin for cloud. And then we just adopt the word nebula for these interstellar collections of gas and dust. In the surrounding nebula, as electrons recombine with H ions, not to be protons, they're protons. So UV comes along, ionizes an atom. So we've got a bare proton, we've got a free electron. Well, that free electron's going to finally find some other proton that's all lonely because some UV stole its electron, some photon kicked its electron off. And so they're like, oh, you know what, let's get together and make a hydrogen atom. And so they do. So as E minus combine with H ions and are captured into high energy orbitals. Using that captured straight into the ground state. I guess I'll just say captured into excited state orbitals. Recombination radiation is emitted as they drop towards the ground state. Too low for me to write. Including the Balmer series. And hence, pretty in pink. They get all pretty in pink because of Balmer series photons being emitted by many, many H atoms as the electrons, having been recaptured, drop towards the ground state. And if they go through n equals 2 on the way down, you get the Balmer series emission line. Lots and lots of atoms doing that together. Ooh, pink, because that's what they combine to, U by U and I. Unfortunately, if you look at the Orion Nebula through even the Perkins telescope, or even the largest telescope in the world, visually, it doesn't look pink because our eyes aren't sensitive. We need to have a longer exposure photograph in order to capture enough light to show the color. And yet, Orion Nebula is very lovely through the Perkins telescope. What photos can't capture is the ephemeral quality of the light when you see it through visually. And it has kind of this soft greenish glow, which I think is partly also due to an oxygen spectral line, as a matter of fact. Our eyes are more sensitive to greenish light, so you can see a slightly greenish color to it. Very slow, not just look like it. What questions do you have? Yes?
What's the difference between open, closed, and globular clusters?
So an open cluster is a cluster that is born in the disk of a spiral galaxy. Open clusters do not have the kind of spherical arrangement of the stars that a globular cluster does. A globular cluster has tens of thousands to like 1 million stars in it, whereas an open cluster is more like hundreds of stars within it, and it's not as organized. Open clusters have the full span of ages from born yesterday, literally, which, being born essentially now, to billions of years old. Whereas globular clusters were all born long ago. They were born in a burst, but they were born billions of years ago. They're all billions of years old, and we find them in the halos of galaxies rather than the disks of galaxies. They're not actively being formed now. We'll talk more about that later. That's the big picture difference between them. What other questions might anybody have? Yes, no, sorry, you used up your question. No, go ahead. Yes.
I was wondering how Mitsui recognized all of these objects he classified around comets, given that they would just appear as blobs of dust and against the constellations because they would be shifting.
So, but see, the thing is that it will stay in the same position relative to the background stars, right? So a comet, you can, even while you're watching it with a telescope over the course of like minutes to hours, you can actually see it shifting in position relative to the stars behind it. Whereas these things would not. They're fixed in place, so to speak, visually relative to the stars. So if he observed it the next night or whatever, and it hadn't moved relative to the background stars, it got to be on his list of things that are not comets because a comet would have moved. Yep. Anything else? What other questions do you have? You're allowed to have another. Okay. All right. So, meanwhile, I should have probably put this put this picture before that. So we've got the pink H2 regions, right, or emission nebulae. There are also what we call reflection nebulae, although scattering nebula would be a better name for it. But anyway, they look blue. So a famous example is in the Pleiades star cluster. So the Pleiades star cluster was born in an H2 region that is no longer there. The Pleiades has already been born from it. It's about 70 million years old or so. The O stars have already blown up a supernovae, but there's still some B stars there, which you see in all their bright blueness. By the way, you probably said this before, what's the Japanese word for Pleiades? Subaru, yes, hence the not very looking like the Pleiades logo of Subaru cars. But in any case, the Pleiades just happens to be passing through this dust cloud. It's not associated with their formation. And light from the stars in the Pleiades scattering off of the dust, look how it looks wispy, dusty, is bluish in appearance. Now you might say, the stars themselves are blue, so doesn't that make the nebula blue? And the answer is yes, the fact that the brightest stars are blue would itself tend to make this thing look bluish, but take my word for it, if you do spectrophotometry of the light scattering from the dust and of the stars, why the light from the dust is even bluer than the light coming from the stars is. And even if the stars themselves were not blue, the nebula itself would still look bluish. And so we've explained why H2 regions are pink. We also need to explain why so-called reflection nebulae, which are due to interstellar dust particles, which, by the way, are about the size of particles in cigarette smoke. So they're like a micron or so across, about 1,000th of a millimeter, 1,000,000th of a meter across. Why do they have this bluish color? Why are they just the color of the starlight that is shining off of them? It's the same reason that the sky is blue. And I don't think anybody should be able to graduate from college, much less an astrophysics major, without being able to explain why the sky is blue, to not tell their children that the sky is blue because of its reflecting in the ocean, because that's absolute nonsense. So, audience at home, I'll show the Pleiades again, but you have to just imagine the lovely Pleiades star cluster, because I didn't have this pointed at the screen when I was talking about it. Anyway, the sky is blue, and interstellar nebulae are blue because of the fact that little dust particles or air molecules scatter short wavelength light more strongly than longer wavelength light, from a combination of both Rayleigh scattering and what's called knee scattering, which we'll talk about shortly. So Rayleigh scattering refers to the scattering of light off of the molecules of the air, and can be extended to scattering from particles up to about 1/10 of the wavelength of light. So that would be, so in other words, knee scattering plays an important role too for particles that are bigger in size than about 1/10 of the wavelength of light. Knee scattering isn't as strongly wavelength dependent, but it still preferentially scatters shorter wavelengths. So this is a description of the intensity of Rayleigh scattered light off of a little particle or a molecule in terms of the angle away from the direction of the incident light. So it's I naught, the incident intensity, times stuff over lambda to the 4th power times 1 plus cosine squared theta gives you the angular dependence. And the big deal here is that 1 over lambda to the 4th power, right? So shorter wavelengths, there's a greater amount of scattering of the light. More photons scatter into different directions from the one they were originally heading in. And it's a much stronger effect at shorter wavelengths. So that means that in the visible spectrum, well, you know, what's the short end of the visible spectrum? Is it red-orange or is it blue-violet? Blue-violet, right, is the short wavelength then. And so blue-violet photons are scattered much more strongly than red and orange photons are. Or in general, short wavelengths are scattered a lot more than long wavelengths. Or the way we tend to summarize it is blue light is scattered a lot more strongly than red light is, which is short for shorter wavelength light is scattered more strongly than longer wavelength light. If the wavelength were half as large, what would happen to the amount of scattering? If you cut the wavelength in half, the scattering would be increased by a factor of what, according to this 1 over the lambda 1/4 dependence? To the 4th, right? 16 times more. Now, the shortest wavelengths are 400 nanometers, which isn't quite half, so that we can see, not quite half of 700 nanometers, but still, it's a very large effect comparing red light versus blue light in the visible spectrum. Blue light is scattered much more strongly. This is why the sky is blue. So it's also why, along with this knee scattering we'll talk about too for larger particles, why a reflection nebula looks blue, why an interstellar cloud of gas and dust will look bluish in the light scattered from all the dust particles. So an interstellar cloud often looks blue due to short wavelength light scattered by microscopic dust particles in the cloud. So in this cartoon picture, here's a star. Here is an interstellar cloud with dust particles in it. And we just pretend it's all either red photons or blue photons. Again, it's really all colors. But think of looking at a star both through the cloud, as illustrated here, point your telescope at it, but also looking at the light scattered by the material in the cloud as opposed to looking at the star through it. And so as illustrated here, the red photons have a much easier time making it through the cloud than the blue photons do. What do we see the cloud by? You see the cloud by light that is scattered off the dust particles. If no light is scattered off the dust particles, you would not see the cloud at all. The only way you see something is when the light reaches us, right? And so I'm off over here, and I'm getting these photons scattered off the dust particles, and I get a lot more blue ones scattered off the dust particles than red ones, and more purple ones than orange ones, etc., etc. So I see primarily shorter wavelength photons scattered off the cloud. Why? Shorter wavelength means it's going to look blue as a result of that. Now, a very smart question. I think XKCD had something, did a riff on this one, says, well, how come it doesn't look purple then? Because purple, actually I should say violet. Purple's like red and blue combined, I think, but violet. Violet wavelengths are shorter than blue wavelengths, so how come it doesn't look violet instead of blue? What do you think the reason is that for that? Yeah.
Stars aren't coming off as much violet light as blue light.
Yeah, it can be, if it's a hot enough star, these H stars would be hot enough, and these stars, their spectrum peaks in the ultraviolet, so from that standpoint, it actually are a good source of violet light. But in terms of, and so that can be part of it. Like for the sun, it doesn't give off as much violet light, if you will, as it does blue light. For a hot star, it actually can give off a fair amount of violet light. Although I'm not sure, like, you know, the range of the spectrum versus the range of the blue, you know, you have to also account for that. So that can be an ingredient for sure. What about the human eye? What about our eye sensitivity? Yeah.
Does it go in the ultraviolet spectrum and we cannot see it?
No, that's not it here. No. So if you had ultraviolet eyes, sensitive eyes, you'd see a lot of ultraviolet light scattering off of these things. This is true. But, yeah.
Is it just like the wavelength sensitivity falls off, like around there? And
Yeah.
it's more blue?
Our eyes are more sensitive to blue light than they are to violet light for that matter as well. I mean, our cones, they're long, medium, and short. They used to say RGB, but that's not really the greatest description because their spectral curves are really quite broad. But our eyes are more sensitive to blue wavelengths than they are to violet wavelengths, and that plays a role as well in the blueness of it. So on the whole, then, we see them as bluish because of the preferential scattering of short wavelengths versus long wavelengths. Makes sense. What questions do you have? Yes?
Does it have to do with the opacity of the interstellar cloud that we see different colors of different objects?
So we will talk about interstellar reddening in a moment, where the opacity depends on wavelength. And that's why stars always look redder than they really are when we see them, because there's interstellar dust that is removing more short wavelengths from the light coming our way than long wavelengths. And so as a result, there is a greater portion of longer wavelengths in the light we receive than is actually coming from the object. That's the flip side of the coin. In other words, the exact same physics, the preferential scattering of shorter wavelengths compared to longer wavelengths, is responsible both for the bluish color of a reflection nebula. Hey, audience at home, look at the beautiful Pleiades reflection nebula there with all that bluish color there. It's also responsible, oh, sorry, before we get there, look, here's some more examples. So here you can see a reflection nebula, NGC 2023. Meanwhile, here's NGC 2024, which is an H2 region. This is, by the way, this is Orion's belt, right? There's the 3 stars of the belt. Why, if we only had eyes sensitive enough to see what we see with a deep, long exposure, gosh, it would be fantastic. That's how beautiful Orion's belt really is, but our eyes couldn't really see all that, but it's real. Here is the Horsehead Nebula, because it looks like a little seahorse or a little horse's head there, the famous Horsehead Nebula. That is a dust cloud where there's enough dust there that very little of the light incident from behind it makes it through the dust cloud, so it looks dark as a result of that. So it's a matter of degree. If there's a lot of dust and not many stars nearby, it just looks like a dark region. Whereas if there's a star nearby, scattering of light off of that dust gives you a bluish reflection nebula. And there's lots of that here, right? There's lots of reflection nebulosity in there. So you should be able to explain why the pinks and why the blues, right? Why the pinks, why the blues. The pinks because of the Balmer series lines emitted by recombining electrons and protons in H2 regions. The blues because of the preferential scattering of short wavelengths compared to long wavelengths by the dust particles. And it's the scattered light by which we see the dust. I'll pause while folks are writing that idea down. Yes?
On the previous slide in the picture, are those also the reflection nebula, like the thing kind of directly above the middle star? It's like
So like this,
Yeah.
this, those are definitely reflection nebula, yes. Yep. Yep. Reflection nebula, all over the place. Yeah. Right, in a region of the, now there's no such thing as a truly dense region of the interstellar nebula, of the interstellar medium. All this gas here is a better vacuum than you could produce in a laboratory on Earth. The reason why you can see it is because even though it's practically a vacuum, we're looking through light years of it, and it adds up when you look through light years of material. In one of the Star Trek movies, Star Trek II, The Wrath of Khan, they go hide in the Volterra Nebula, which is, so it's pink. I guess they got that part right. The lightning flashes or whatever, no, not a thing. You couldn't hide a ship in a nebula. If you were in the middle of the Orion Nebula, don't take off your spacesuit because it's a better vacuum than you can make on Earth. And there's not a lot of oxygen in that almost vacuum anyway. And also, you can see for light years. You would see this faint glow everywhere because you're looking through light years of hydrogen glowing, but the visibility is light years within this thing. It's ridiculous to hide a ship in one of these things. That makes no sense whatsoever. Just like asteroid fields are not a thing, right? Where they're like, you can fly through the asteroid belt and not have any chance essentially of being hit by anything. It's very safe to fly through the asteroid belt. It can be very far apart. Okay. The flip side of the blue colored reflection nebulae is interstellar reddening. When we view a star through an interstellar cloud, the star looks redder than it really is because, again, the dust scatters short wavelength photons more than long wavelength photons. And in this case, they're being scattered out of the beam of light that is heading to us from the star. So a larger fraction of the long wavelength photons reaches us. And so that's illustrated here. So think of it like this. When you see a star through a dust cloud, the star looks redder because of blue photons being preferentially scattered out of the beam and red photons making it through. Well, those blue photons being scattered out of the beam by that dust are the ones that you see the cloud by if you're looking at it from the side. And so it's two sides of the same coin. Interstellar reddening and the blue color reflection nebulae are two sides of the same coin. They both come down to the preferential scattering of short wavelengths. It's a matter of, are you looking at the starlight that makes it through the nebula, or are you looking at the light scattered by the nebula from nearby stars? What questions do you have? Yes?
So let's say we were to look at Pleiades from a different angle. It would look different in color?
So if we go back to the Pleiades here, the stars are so freaking blue that they still look blue even through the dust. However, if again you did a detailed spectrum, right? Like if you look through, or even if you took a photograph through the B photometric filter and the V photometric filter and found the magnitudes to find the B minus V color index. If you could magically remove the dust, the B minus V color index would be smaller, i.e. bluer than it is when we see them through the dust. So just because something is reddened doesn't mean that it looks red. It just might not, if you will, as blue as it really is what it comes down to. And so those stars are reddened. They're still blue, but they're reddened by the dust in between us and them. They're not as blue as they would be if the dust were not there. Does that make sense? Okay. So here's, I like this photograph right here. It shows a very distinctive example of interstellar reddening in action. Interstellar reddening makes the more distant H2 region on the left appear redder than the closer H2 region on the right. This one's further away, so there's more dust between us and it than there is for the one on the right. And so think of this in terms of the Balmer series spectral lines. For this one versus this one, think of the teal and the indigo lines, in which case is a greater fraction of the indigo and teal Balmer spectral line light getting through. Is it the one on the left or the one on the right? More getting through from the teal and indigo transitions. Yeah, the one on the right, more of that light's getting through. The one on the left, then, looks more the color of Balmer alpha, the red spectral line, because the other ones have been dimmed a lot more than it was. All the spectral lines are dimmed. Every wavelength is dimmed by the dust, but the shorter wavelengths are dimmed more. And so the light we receive from this more distant one is more strongly composed of just the Balmer alpha line. And so it looks more the color of the deep red color of the Balmer alpha line. Makes sense? What questions do you have? I think that's a beautiful example of interstellar reddening in action. Now, here is a dust cloud which is thick enough and has enough dust in it, it's got a greater density of dust than some others do, that it's actually opaque to visible light. It looks like a hole in space, but it's not that there's any stars missing there. It's just that the optical depth, remember that word? The optical depth along the line of sight for this cloud is large enough, much larger than 1, such that essentially no starlight is making it through it at visible wavelengths. But what might happen if we look at infrared wavelengths? Infrared wavelengths, should they have a harder time or an easier time making it through a dust cloud than visible wavelengths, and why? Easier because longer wavelengths. Yeah, longer wavelengths don't scatter as much. So infrared wavelengths are able to make it through dust clouds more readily. Here's an infrared photograph of exactly the same cloud. Of course, it's been false colored. You know, our eyes can't see infrared, but sensors can. So infrared light penetrates the dust cloud due to its longer wavelengths, revealing protostars embedded within the cloud. Those are stars being born inside of it. Some of them will be stars behind it. But some of them are protostars being born inside of it, and we can see their light. This is why astronomers who study star formation like to use infrared telescopes like JWST. JWST is an infrared telescope. Infrared light penetrates dust much better than visible light does, and it lets us peer inside things like star formation regions. We can see protostars being born within their dusty cocoons much more readily than we can in visible light. Ooh. Here's the Orion Nebula in visible light on the left from the Hubble Space Telescope, and from the ground-based Very Large Telescope, the VLT, in infrared light on the right. Notice that you can see lots of cute, giant baby stars being born in the Orion Nebula. The star cluster in formation being born within the Orion Nebula when we look in the infrared. Beautiful, isn't it? Lovely, indeed. Here are extinction curves, by which we mean, in other words, by interstellar extinction, we mean how many magnitudes dimmer is the light than it would be without the dust being present in between us and the line of sight. Here are extinction curves along the line of sight to 3 stars. So this is the dimming as a function of wavelength divided by the dimming in magnitudes through the V filter. Right, so it's a ratio there. It's a very large range of wavelengths. It's actually reciprocal wavelength plotted here. So here are the U, B, and V photometric filters. So this is way off into the infrared over here. And so one thing you can see is, or well, sorry, this is V, B, and U, but blue, violet, stop, visual, verde, green, right? The visual filter, the blue photometric filter, and the ultraviolet photometric filter, is the fact that this is sloping upwards as we go from V to B to U. Is that consistent with what we've said about scattering by dust particles? And if so, why? And if not, why not? Is that consistent? Yes?
What does the A lambda and A mean?
So it's the amount of extinction, the amount of so how much dimming in magnitudes at the wavelength in question. And so A sub lambda over A sub V would be the dimming for that wavelength divided by the dimming through the V filter to normalize it. That's why the V filter is at 1 there. In other words, the dimming through the V filter divided by the dimming through the V filter is 1. The dimming through the V filter, more or less than through the V filter. More, right? How about through the U filter? More or less than through the V filter? More. Is that consistent with what we said about the scattering of different wavelengths by dust particles? Yes, because this is saying there's more dimming through the B filter, which is overall shorter wavelengths than the V filter, and even more dimming through the U filter than through the V filter. There's 3 curves because we're looking at 3 different stars, and so there is a bump in those curves that has been interpreted as being due to graphite. In other words, if you have dust particles that contain graphite, which is carbon layers, right? Polymer carbon, like little carbon layers, like in pencil lead, essentially. You would expect there to be a bump because it's good at absorbing those infrared wavelengths. And so, because astronomers try to infer, well, what the heck is the dust in the interstellar medium made of? The answer seems to be that there's silicate grains. What are silicates? Name something that's made of silicates that is in your everyday life.
Is it the stuff that you get when you buy something new that absorbs water?
No, that's silica.
So that's what.
That's silica. I'm talking about what are natural things that tend to be rather silicaceous. What's that? Yeah, silicaceous. Lots of silicates in there. Natural things that are very silicaceous. Lots of silicates. Silicon oxygen compounds. Things that have silicon and oxygen in their molecules. Yeah. What are things that tend to have a lot of silicon and oxygen in their chemical makeup? Yes?
Sandpaper?
True. True. Very true. Yes, quartz is silicon oxide compound, right? Or in general, I think you'll be awesome if you can answer this question. Or in other words, if you are awesome, you could also say that, wow, you really were rocks! Yeah, rocks are rather silicaceous, right? So minerals, right? Minerals. So the interstellar medium little particles seem to be, some of it is little silicate particles, little mineral particles that can be coated with graphite, producing a bump like that in the absorption profile. And they can also have, under the right conditions, if it's cold enough where they are, ices, where ices mean hydrogen compounds that form ices at low temperatures. So in other words, you have water ice, methane ice, ammonia ice. And again, a typical size seems to be something like the size of particles in cigarette smoke. Yes? Stars. So in other words, they're forming, stars form carbon in their interiors, right? And also they're born from carbon. You can have some stages in evolution where dredge up in the core, convection can reach down in the core and bring carbon up to the surface that was formed in the core during helium burning. And then if that escapes into space, because these can have like strong stellar winds associated with them, that can condense into dust specks. So the interstellar means the dust in it seems to come from the atmospheres of stars that are losing a lot of mass through wind. It cools down enough in the outer atmosphere that you can have particles starting to form. It's not entirely understood where the material in the ISM comes from. That's an area of active research, but giant stars, low mass stars, seems to be a source of it, as a matter of fact. Yeah. Where was I headed with this? To say it's time for break. Yes? No, because I ran out of copies, so we'll print one off. No, I've got it. What's that? Okay, but then I'm going to print one and give it to you. I mean, yeah, I'm just going to print another one. It seems like the thing to do.
Okay. Could you also post it on Blackboard?
What's that?
Could you also post it on Blackboard?
Oh, yeah, I should. I think I just forgot to.
You're gonna get bit by it.
Alrighty. By the way, there's 3 curves there because it's 3 stars. And, the dashed line is the observed computed as they compute what they think it would be versus a model of based on a model of the composition of the dust. And, clearly we are seeing Herschel 36 through less dust than we are BD plus 56 504. Different 3 stars, different amounts of dust in between us and them. Anyway, I mentioned before that there's also what's called me scattering. Me scattering for molecules and tiny particles less than 1/10 of the wavelength of light is predominantly Rayleigh scattering, but for particle scattering, where particles are like, more like a wavelength in size, me scattering predominates. This scattering produces a pattern like an antenna lobe with a sharper and more intense forward lobe for larger particles. In other words, Rayleigh scattering, you get scattering backwards in the same direction light was coming, just about as strongly as scattering forwards. For me scattering, there's more forward scattering than there is backward scattering, and it tends to be forward scattering as opposed to off on the sides. It's not so strongly wavelength dependent, and so it produces the almost white glare around the sun when a lot of particulate material is present in the air, and it's also why mist and fog do that white light. It's scattering from the little water droplets are considerably larger than the little dust specks are. So, while I am by no means encouraging you to smoke in order to demonstrate this, I certainly would not. I said that the interstellar dust particles are about the size of the particles in cigarette smoke, small enough that there is that wavelength dependence of the scattering. If you look at the smoke coming off the tip of a cigarette, have you ever noticed it looks a little bit bluish in color? Have you ever noticed that before? If you haven't, put on a gas mask and go up near a cigarette and light it and look at the smoke coming off the tip. It's got a little bit of a bluish character because of Rayleigh scattering, because it's preferentially scattering blue light. But if a smoker goes, you see the smoke coming out of the smoker's lungs, that looks white. Why would that look white as opposed to blue? What's going on there, would you say? So the blue is Rayleigh scattering. When it comes out of the lungs, the material coming out of the lungs is more me scattering. Why would that be? Yeah.
The smaller particles are like absorbed and then bigger ones don't get in the lungs or something?
Could be part of that, but also, if you're on a cold day, you go, you quote unquote, see your breath. What are you seeing? Water vapor, right? You're seeing water vapor condensing in the cold air. The smoker breathes out, there's a lot of water vapor in there that come from the lungs, and so you get knee scattering from, little water droplets, I guess, if you will. And so you get a whiter look to it as opposed to the blue. Again, I don't encourage you to demonstrate this yourself. If you already smoke, okay, go ahead and do that. And then having fulfilled the purpose of smoking in order to see this effect, stop smoking. It's just not just after that. So Rayleigh and knee scattering by the atmosphere. In other words, we've been talking in terms of interstellar nebulae look, dust clouds look blue, and there's interstellar reddening. We've been putting it in terms of outer space. But it's a very down-to-earth phenomenon too. The sky is blue and sunsets are red because of Rayleigh scattering. So if you consider, if the Earth had no atmosphere, what color would the sky be? Yeah, also known as black. Yeah, it would look black, right? Because photons from the sun that flew over your head would keep on flying if there's no atmosphere. But if there's air molecules there, then some of those photons, which are going to fly over your head and never enter your eye, are going to scatter off air molecules and enter your eye. And short wavelengths are scattered much more efficiently than long wavelengths are, and therefore the sky is blue. When you see the blue sky, you are literally seeing the air. That's what you're looking at. You're seeing the air. Now, do we see the air in this room looking blue? No, because it's kind of like with the interstellar material. You have to look through light years of it for it to add up and have a distinctive effect. The air in this room is preferentially scattering blue light too, but I can see to the back of the room. There's not a whole lot of light getting scattered by the small amount of air in this room. But when you look through miles and miles of atmosphere, that adds up, right? The atmosphere is, it just fades away, but roughly speaking, it's like, it's about 100 kilometers thick, roughly speaking. You look through many kilometers along the line of sight, and that adds up. So when you see the blue sky, you're seeing the air, and it looks blue because of the preferential scattering of short wavelengths by the air molecules. This is why the sky is blue. It's not because it's reflecting the ocean. Please don't believe that. Please tell your parents, right? Justify your tuition by telling your parents why the sky is blue, and it's not what your dad or mom might have told you at some point if there's anything about reflecting the ocean. If anything, the ocean when you're at the beach looks blue because it's reflecting the blue sky. It's the other way around. You're seeing the blue skylight reflecting off the ocean water that gives it the blue color. Does that make sense? I want you to be able to explain that for sure. Every astrophysics major should be able to explain why the sky is blue, right? So from overhead, Rayleigh scattering is dominant, the me scattering intensity being projected forward. Since Rayleigh scattering strongly favors short wavelengths, we see a blue sky. Take out the air molecules, and those photons scattered towards the observer don't get there, and you see a black sky. You only see light that actually gets into your eye. When there's large particulate matter in the air, say from cars, volcanoes, whatever, the forward lobe of me scattering is dominant. Since it's not very wavelength dependent, that's why you see a white glare around the sun during the day. You're seeing me scattering by dust in the atmosphere. The more there is, the bigger the region around the sun that has that kind of white glare around it. Okay? Makes sense. Does it make sense? Any questions about that? What questions do you have? Yes?
You just once over me scattering again. I don't think I...
Yeah. Okay. So me scattering is for particles that are more like a bit larger than the wavelength of the light. Okay. And with me scattering, so what these arrows represent is the intensity of the scattering in different directions. right? So in other words, think of a whole beam of photons that are all going this way. The length of the arrow is proportional to the fraction of the photons that get scattered in that direction. And so the idea is a very small fraction of the photons backscatter, go back along the same direction they were. Not too many are scattered at 90 degrees. More and more are scattered such that they're traveling in essentially almost the same direction they were going in the first place. So there is scattering though. So in other words, you are still losing light from the beam, and you will think of a particle over here. Okay, here's a photon that was going to miss the observer, but it gets me-scattered towards the observer. And so because of the strong forward scattering, there's only a small angle around the sun where there's a lot of me-scattering into your eyes from molecules that are a little bit off axis, a little bit off the beam of light coming from the sun. And so because of that, you see most of the me-scattering near the direction of the object that the light is coming from. Over here, the me-scattering is forward. There's very little me-scattering towards you of light that is coming from the sky far away from the sun, so it's not a very big effect. But light that is coming from nearly the same direction that the sun is from us, why a lot of that will have been, here's a photon who's going to miss us. Oh, I got me-scattered at a small angle. And so there you see me-scattered whitish light in a region around the sun. The further the angle away from the sun, the less you see, because that's a bigger and bigger angle of scattering, and me-scattering is mostly forward scattering. Hence the white glare around the sun. Meanwhile, in the rest of the sky, Rayleigh scattering on a clear day, if it's clouds, it's different. But on a clear day, Rayleigh scattering dominates away from the sun, and so you see the blue sky as a result of that. Meanwhile, as you look at the sun at sunrise or sunset especially, but even in the day, the sun looks redder than it really is for the same reason of interstellar reddening. In other words, light that's getting scattered out of the beam by the atmosphere, light coming to you from the sun, where atmospheric molecules and dust are scattering out of the beam, why it doesn't reach you. The light that reaches you from the sun is preferentially longer wavelengths. And so the sun looks redder than it really is because of looking at it through the atmosphere. Now it's very important. Sometimes I have to emphasize, so the physics is the same as interstellar reddening, but interstellar reddening is not what makes the sun look red at sunset, because we are not looking through interstellar clouds at the sun at sunset. We're looking through Earth's own atmosphere. Sometimes I get that when I'm teaching intro astronomy. I'll get explanations from people. It's like, oh, an interstellar reddening causes the redness of the sun at sunset. No, don't say that. That's not interstellar reddening. It's the atmosphere. Our atmosphere and interstellar space are very different things. But anyway, I'm going to count on you not to get that confusion. Okay, here's a kind of a ridiculous diagram, because apparently the sun at noon is high overhead in Alaska, according to these folks. Okay, that detail's wrong. Ignore that little detail. But the point is that due to the curvature of Earth's atmosphere, when the sun is high in the sky, you're looking literally through a shorter path of air than when the sun is lower in the sky, so that the light is skimming along the ground. You're looking through a longer path of air. And so all these effects are enhanced near sunrise and sunset, where you're literally looking through a longer length of atmosphere, so that a greater amount of scattering occurs. So the sun is always reddened by the atmosphere, but it's especially reddened when it's closer to the horizon, because you're literally looking through a longer path of atmosphere. We tend to think of the sun as being yellow, but astronauts report, and I agree with this when I look at when I'm in an airplane at high altitude, from the ground the sun looks a bit yellow for a couple of reasons. One is it's always reddened, especially though, when do we tend to look at the sun more? When it's high in the sky or when it's closer to the horizon? When it's close to the horizon, there's more reddening. If you're in a high altitude plane or in space, it looks pretty much pure white. The sun is really white in color more so to the human eye. The yellowness comes from us looking looking at it through the atmosphere, essentially. And the effect is biggest at sunrise and sunset when it can be so extreme that the sun actually looks red or orange, essentially. It also looks a lot dimmer too, right? Because interstellar reddening is also interstellar dimming. Atmospheric reddening is also atmospheric dimming because less light is making it through at every wavelength. So the sun looks dimmer as a result of seeing it through the atmosphere, especially at sunrise and sunset, especially if there has been a volcanic eruption, for example, that puts a lot of extra particulates into the atmosphere, or if there's a lot of air pollution that puts a lot of particulates in the atmosphere, there's more dimming. Now, I will tell you that I have stared at the sun when it's nice and dim at sunrise and sunset, and I've never hurt myself. But I will say, if it's still pretty bright, you can look at it and it's not painful, but you're noticing it's still pretty bright, it's probably not a good idea to stare at it then, because why? Well, what about the infrared light? If you could look at the sun with infrared light at sunrise or sunset, would the effect we're talking about be bigger or smaller at infrared wavelengths? At infrared wavelengths, so the sun looks dimmer because of photons being scattered out of the beam of light coming at our eyes from the sun. At infrared wavelengths, more scattering or less scattering? Less scattering, right? Less scattering. So the sun getting dimmer as it approaches the horizon is less pronounced in infrared wavelengths. And your eye doesn't have pain receptors. And so, in principle, you can have infrared light burning your retina when it's not painful to look at the sun at sunrise or sunset. I don't know if that ever happened to anybody. Certainly never happened to me, but at least in principle, not a good idea to stare at the sun at sunrise or sunset even, because more infrared light is getting through invisible light. But you can't perceive that. You can't see infrared wavelengths. So just a little caution there. So here's my beautiful illustrations of why all this happens, which are terrible, but they're better than the ones I used to make by hand. People made fun of me, so I made these instead, jokes. I mean, they're still not the best, right? Same idea here. Light reaching your eyes after being scattered by the atmosphere's mostly short wavelengths, so you see the sky is blue color. Now, most of the light scattered, it doesn't enter your retina, but a small portion of photons scatter into your personal eyes, and you get to see them, and that gives you the blue appearance of the sky. Again, you're literally seeing air when you see the blue sky. Take away the air, you'd see a black sky. You're seeing the air when you see the blue sky. You see light scattered off the air. You're literally seeing air when you see the blue sky, which is kind of interesting to think about. And so we see the blue sky. But if you think about the light coming to us from the sun, light reaching your eyes directly from the sun at sunrise or sunset is mostly long wavelengths. Since the short wavelengths get scattered in other directions, so the sun looks red. So just as the blue color of reflection nebulae and interstellar reddening are two sides of the same coin, Rayleigh scattering by small dust particles in the interstellar medium, the blueness of the sky and the redness of the sun at sunset are also two sides of the same coin, that coin being Rayleigh scattering by air molecules. In both cases, by atmospheric air molecules, in both cases, the same phenomenon is responsible for both. They're two sides of the same physics coin, so to speak. What questions do you have? And again, gosh, I probably want you to be able to explain these analogies with interstellar reddening, blueness of reflection nebula, blueness of the sky, redness of the sun at sunrise and sunset. I want you to convince me that you understand all that. Because I'll be damned if you're going to tell your kids someday that the sky is blue because it's reflecting the ocean. You're not going to do that. If you do, I will hunt you down. Okay? Here's a lovely example taken by me over Lake Erie from Geneva on the Lake. My wife and I stopped there on the way back from a wedding in Boston. We basically kind of took a wrong turn and we're like, oh crap, well, here we are near Lake Erie, maybe there's a place to stop and have a nice view. And my wife looks on her phone and said, oh, Geneva on the lake's nearby. And I'm like, we're going. So we went there and we stayed for many hours and were treated to a really lovely sunset over the lake. So I have lots and lots of photos of the sunset over the lake where, why, can you see the reddening of the sun by the atmosphere, right? And then another piece of it is, well, the sky near the sun is also red, right? Well, the idea there is if there's not too much dust, et cetera, in the atmosphere, well, then the sun itself could look pretty red, but the sky nearby still looks pretty bluish. But if there's a lot of scattering going on, then what can happen is that by the time the light is kilometers away from us going through the atmosphere, there's very little blue light left going through the atmosphere towards us. So that atmosphere also looks red just because so little blue light got to the atmosphere near the sun along the line of sight. So the whole area can look red as a result of that. Not enough blue light is making it through to within miles, kilometers of where we are. And so you can have a whole region around the sun that looks reddish because very little blue light has made it to the nearby atmosphere to scatter and look red and then look blue to you. Yes?
So if the atmosphere is like much thicker than it is now, and like to the point that it was the same thickness of atmosphere as it is like at sunrise and sunset, then would the sky always be red?
If it were thick enough, you could get to the point where, yeah, the sky would tend to look red, just because very little blue light made it down to the lower levels of the atmosphere. So in an extreme case, really thick atmosphere, you could have a whole sky that looks reddish. The surface of Venus is always a yellowish-orange color, and that's because its atmosphere is so thick that the blue light never makes it close to the surface. And so as a result, the whole sky looks a bright yellowish-orange color because only yellowish-orange light, longer wavelengths, are making it anywhere near the surface. And so the sky, the light you see scattering from the sky is that light. The air molecules are scattering that light because there's no blue light making it for them to scatter in your direction. So Venus is an example of that. The entire Venusian sky and the landscape are all this yellowish-orange color just because the air is so thick, 90 times Earth's atmospheric pressure, that blue light just doesn't make it to the surface in any abundance whatsoever. It's also hot as hell and crushing, so you won't be able to enjoy the view, but we have pictures. Yes?
So, I think it's really going to really put the sky
So I guess it's going to depend. It's going to depend. Well, so if it does get very polluted, it actually tends to make the sky look less colorful and whiter because of additional de-scattering, because larger particles, in particulates from pollution, aren't scattering the light with as much wavelength dependence as molecules and smaller dust particles do. So you may have noticed on a very polluted day, the color of the sky is washed out because of de-scattering.
So what would like, because I know like some days it's like super blue.
Yeah, so when the atmosphere is very clear is when it's super blue, because then there's not as much dust to pollute the light with white de-scattering as opposed to blue Rayleigh scattering. So a very clear sky tends to look super blue. So when I was in graduate school, I had a good friend from Toledo and another friend from California. And the friend from California didn't believe me and Jim when we said that we can look at the sky from like inside a building and look at the sun, right, and the color of the sky, and decide it looks like it's a cold day today. And our California friend just didn't believe that we could do that. And Jim and I were thinking about, so, well, what makes us think that it looks like a cold day today? And what we decided, and maybe we were even right, is cold days tend to have very clear air. And so if the sun has less white glare on it, around it, and the sky is very pure blue, it's more likely to be a cold day because for whatever reason, I'm not sure exactly why, there tends to be less particulate pollution in the air on cold days. And so we Midwesterners interpreted that as it looks cold today without really thinking about why. But I think that's what we were picking up on essentially.
Because in the summer you have all the air quality or something.
Yeah, there's more AQI, air quality alerts in the summer, and the sky doesn't look as blue at those times. Yeah. And at sunset, the sun can get very dim and easy to look at, and so forth. Right? Very dim, even a very deep red in color. I've seen some exquisite blood red moons before on days where there was more pollution and so forth. Meanwhile, and I think it's the next slide, one of my favorite photos from the space missions, any space mission, is here is a photograph of a sunset on Mars, photographed by the Spirit rover. I love this photograph. One, because I'm looking at a sunset on freaking Mars. I mean, what I really like to do is really be freaking looking at a sunset on freaking Mars because I'm standing there. I'm not counting on that. I wasn't born in the proper century for that. Nevertheless, I was born in a century where I can get postcards from Mars, actual photographs from Mars, right? Can you imagine showing this to somebody 100 years ago? Here's a postcard from Mars. And they'd be like, what's a postcard? Okay, we explain that. And then they're like, and it's from Mars. They're like, witchcraft! You know, right? It's like, oh my God, right? This is a postcard from Mars. So the Martian sky, as you may know, is red rather than blue. And that's because the Martian dust has lots of iron oxide compounds in it, similar to rust. Rust is a form of iron oxide, which is a reddish color, reddish brownish color. The Martian atmosphere is very thin, less than 1% the density of Earth's atmosphere, but it's dense enough that winds can kick up dust particles from the soil, and those dust particles, because of the iron oxides, are pigmented, they're colored. Dust specks in our atmosphere tend to not have any intrinsic color to them really, but the Martian dust specks are colored. And so that means that they scatter red light more than they scatter blue light because they are pigmented. So they preferentially reflect redder wavelengths than blue wavelengths. So the Martian sky is reddish in color because of those reddish colored dust specks in it. So that's one thing, check it out, red Martian sky. But the sunset is blue. The sun looks bluer at sunset. There's a region of blue around the sun at sunset. Why? Because it's exactly the opposite on Earth. Take this picture and replace all the red arrows with blue arrows and all the blue arrows with red arrows, and that's Mars. More red light is scattered into your eyes by the sky, so the sky is red by those little dust specks. The air itself would look bluish without the dust in it. It would look a dark blue because there's not as much of it. At the same time, again, reverse the colors. The light coming directly from the sun, more of the blue light makes it through because the red dust particles are scattering more of the red photons out of the beam. So blue light preferentially makes it through to the camera, or I wish, to my eyes. And so on Mars, we have blue sunsets in a red sky, instead of on Earth, where we have red sunsets in a blue sky. And I think that is so freaking cool, can I just say? And that's why that's one of my favorite photos from space, essentially. And there's also ones you can get where you can see like movies of Martian sunsets, and you see the sun getting bluer and bluer as it sinks down and so forth. And I'm like, I'm in an upside down world here on Mars. It's just like, you know, so reverso physics there, all right? Is that cool or what? Ooh, that should have been much more convincing. We're going to do this again. Ooh, Okay, it's a little better, All right, shall we do the demonstration of all this? Okay, so here we have, let me get the audience at home able to see this well too, or better. And then you can watch it over and over again later. So let's see. it's, yeah, there we go. Okay, that should probably show it reasonably well, except got it wide out so that we can see it on the wall over there. And then I'll turn down the projector. Okay. So what we're going to do is to mute. Where's the mute button? I hit it by accident. Maybe you do. There we go. Okay. Sun or star. And it shines through the water, okay? Not too much is in the water right now, but I have some milk. Milk is not a solution so much as it is a suspension. So in other words, there's little droplets of fat and milk solids that are suspended in the water, okay? And so what I will do is put a little milk in there and stir it up. And the little milk droplets will behave like interstellar molecules or air molecules. They will scatter blue light more than they will scatter red light. And so as a result of that, I can try to get a video here if you like. As a result of that, the light that you see on the wall there should look redder after I put a little milk in there. And we might be able to see that the scattering here, you can see that this beam right now looks white. Well, if what we're saying is true, what color should the beam look like when I got a little milk in there? More bluish, because it's scattering more blue light. So, not sure what the magic amount to add is. I have my old pill bottle full of milk here. I'll put a little in here, and then we'll just kind of keep going. Hope that's not too much already, okay? So, stir, 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 stir. Wow, that was so thorough. It was probably too much already there. So, yeah, but you can actually see. So I actually put more than I wanted to. You can see it's kind of reddish here, right? Because more blue has been scattered out. So by the time you get over here, it's mostly red light there. This is like the red air around the sun at sunset. If not enough, if so much of the blue is scattered out before you even get to the air close to us in the direction of the sun, then what we see is red light scattered from that air. And I can look through here, yeah. So come join me up here and look at the filaments of the projector bulb and tell me, do they look the light color that they really are as you go down and look through that there? Yeah. The correct response, by the way, is ooh. It does, yes. Why, it's almost like physics works, isn't it? Yes. I think the audience at home probably wants to come on a voyage here and see this for themselves. There you go, that's right. There we go. All right, so here we are. We're going to look down the barrel of this, and it's still blown out by, it's auto-exposing. Well, okay, anyway. It's so distinctive as I'm looking at it here, and there must be some manual control of the shutter, but, well, look at the reflection, audience at home, on the table there. Can you see how amazingly orange that is? Ooh, and now I have to turn you off because this thing won't last to the back of the room because it's holding no charge whatsoever. So be back in a moment or in 0 time on the video. And we're back. So once I tried to do this and I forgot to bring any milk with me. And so I just had this powdered milk that I found back there. I thought, oh great, powdered milk. Carnation instant milk. Well, I get into it, and it's all like orange to begin with. So I'm like, well, this is not going to be very convincing if I put orange powder in there. Oh, look, it's making the light redder. It's orange powder. So then I look at the expiration date, it's like 1977. It's like, I'm surprised I'm still alive. But in any case, all right, back to our story. Unaged. Yeah, and then, what's the next one? Oh yeah, talk about that too, right, which Anushka just managed to photograph herself the other day. Yeah, so did you know, as every astronomer should, that you can see the Earth's shadow just after sunset and just before sunrise? Why, yes, you can. I have a photograph to prove it that I took. I think this was in October of 2024 when we took this. So, right there. You can see where this is, right along Sandusky Street. So, there's the moon. So one thing is, what phase is the moon there? Pretty much full, right? So full moon means we're seeing the lit side of the moon, and if you think about it, that means that the sun and the moon are on opposite sides of the sky, so that the lit half of the moon is turned towards us. So that means if it's a full moon, if I point to the sun in one direction, 180 degrees away should be where the full moon is. This is right after sunset, so it actually is making a lot of sense that the full moon rose right about that time. It's not always a perfect match in terms of the time of rising because of the tilt of Earth's axis relative to the plane of its orbit and to the fact that the moon's orbit is tipped and so forth. So, but at a perfectly full moon, they'll really be 180 degrees away from the sky, but that doesn't mean they'll rise and set exactly 12 hours away from one another because they can have different declinations, different north-south locations on the celestial sphere. But anyway, it's still going to be close. A full moon always rises around the time of sunset and sets around the time of sunrise. So you can see that here. Meanwhile, and now go see this for yourself. You might have noticed this before, but go look for it. For a while after sunset, low down in the sky, it's a bit of a deeper bluish gray color than higher up. That is Earth's shadow that you're seeing. In other words, if you were in an airplane in this air, the sun would be below the horizon for you, whereas if you were in an airplane up here, the sun would be a little above the horizon, right? You go in an airplane, go high enough, and you can bring the sun back over the horizon for you. And so this air is illuminated by direct sunlight, and this air is not. It's still illuminated by light scattering from the ground, or reflected from the ground, and scattered from the rest of the atmosphere. So it's not completely dark for sure, but the sun has set in this air right here, and so it looks darker. There's less light there. In other words, you're literally seeing Earth's shadow in the air. And it's cool because, watch carefully, as time progresses, the border keeps getting higher and higher, which makes sense. The sun's getting further below the horizon, so the shadow is climbing up higher and higher above the horizon. So around like half an hour so you can still see the shadow, and then it starts to get so dark that you can't tell anymore. But in the end, really what's happening, right, is Earth's shadow rises and fills the entire sky, and then it's nighttime, right? That's what's really happening. Right around sunset, you're seeing the beginning of that. Or right before sunrise, you see the end of that. You see the Earth's shadow slowly descend to the horizon on the opposite side of where the sun is rising in the east. Meanwhile, and again, look for this yourself, and it's better on a clear day, there's a pinkish region called the belt of Venus, not the planet, the goddess, the belt of Venus that is above the shadow. Why is this region pinkish? Can you think of why that would be? What if you were in an airplane in this air right there? What would you see? You don't get to say because we've talked about this before. It's cheating. Not really cheating, but why would that be? Somebody who hasn't talked to me about this before. Why would that happen? Yeah. if you're in an airplane here, you see the red setting sun. You see the red setting sun, and so there's lots of red light traveling through this air and scattering back towards us. And so basically, if you're in an airplane up here, the sun is still pretty far above the horizon, not looking as reddish. Descend, 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 the sun's getting closer and closer to the horizon, looking redder and redder and redder. So you see more and more, this air is being lit by redder and redder light as we go down here. But now we dip down here and the sun's below the horizon, so there's not as much light, and so it looks darker. Ooh, and it's even better in a plane. Like for example, if you're flying to Arizona, why you might see something like this out your window. As in, this is what I saw out the window. I stitched two photos together, taken a little bit apart, so they don't match exactly. But okay, look, very distinctly Earth's shadow, belt of Venus, and it continues. It actually intersects the horizon over here because no matter what the flat earthers think, Earth is spherical. The shadow is curved, right? So you can see that curvature of the shadow, and this was near sunset, so this is moving east, right? And so, because the way we were flying west, so this is further and further eastward, right? And so you can see the curvature of the shadow, and you can see it intersecting over there, essentially, right? And so, and then also the very more distinctive, the belt of Venus there. Pretty cool, huh? I sure think so, and I command you to think so as well. Okay. Go back there. What questions do you have?
I flew over the bed of Venus, so I saw an extremely red sunset and an extremely blue sky.
Oh, yeah, right, yeah, cool. Yeah, maybe next time I'll dig it up just to show. I took a photograph of the moon, too, and boy, was it flattened, because atmospheric refraction is what makes the sun and moon look kind of oval when they're close to the horizon. And if you're in a plane, you can see them lower down where the effect is stronger. And so from a plane, the moon or the sun near the horizon looks more strongly flattened than it does near the ground. And in space, like from the International Space Station, it just looked ridiculous. It would really flatten as a result. Fun fact is, from the surface, atmospheric refraction, differential atmospheric refraction, causes the sun to be about half a degree lower in the sky in appearance than where it would look if you took away the atmosphere. Half a degree is the angular size of the sun or the moon on the sky, which means essentially that when you see sunrise or sunset, when you see the sun looking like this, the actual sun, if you took the air away, is more like that. In other words, you see the sun fully above the horizon just before it actually starts to come above the horizon, and then vice versa at sunset. The effect is big enough. And it's differential. In other words, the more air you look through, the bigger the effect is. So all parts of the sun's or the moon's image are bent a little higher in the sky than they would be without the atmosphere, but the effect is strongest near the horizon. And so the bottom part of the sun or moon is lifted more in appearance than the top is, which is why it flattens it, which is why it doesn't look circular, it looks oval, because there's a stronger effect near the horizon. And that effect gets bigger from an airplane where you can see the sun or the moon lower down than you can from the surface, right? The surface, you can see it this far down. In a plane, you can see it that far down, so to speak, and so the effect is bigger, and so you see differential, even stronger differential refraction, and then you make Facebook posts about it, so because you want to educate all your friends about what's going on. Oh, that's just me. But anyway, yes, and I'll point out here, right, so, no, I don't want to point that out. No, I was confusing myself. Okay, anyway, what questions do you have? Okay, fun with science. Okay. I want to talk about now what is known as 21 centimeter radiation from interstellar clouds of hydrogen. So interstellar atomic hydrogen, we are able to observe what is called 21 centimeter radiation. And it is caused by the fact that protons and electrons both have that mysterious quantum property called spin. And because it's quantum mechanics, why their spins can't just be randomly oriented with respect to one another. They have to be either in the quantum sense parallel in the same direction or anti-parallel in opposite directions. If the proton is spin up, the electron can be either spin up or spin down in the same direction that the proton is spin up. And it turns out when you analyze everything in detail, there's a little bit of interaction energy due to the magnetic dipole moments of the electron and the proton, and due to some relativistic effects. And when the spins are parallel, you have a very slightly higher energy configuration. And when the spins are anti-parallel, you have a very slightly lower energy configuration. And if you calculate the difference in energy between those two states and convert it into the wavelength of a photon emitted when the electron flips its spin relative to the proton, going from parallel to anti-parallel, the wavelength works out to be about 21 centimeters, or about 1,400 something megahertz. It's about 21 centimeter wavelength. We can't readily observe it in the laboratory because this energy difference is so small. Right, that's a very long wavelength for a photon. That energy difference is so small, vastly smaller than, say, n=1 to n=2 transition for the different orbitals of the electron, for example, that the lifetime of this state, if you just isolate a hydrogen atom and you manage to put them parallel spins, well, water flows downhill, quote unquote. Eventually, the electron will spontaneously flip its spin to get into the lower energy anti-parallel configuration. And the mean lifetime for that, the average lifetime for that, is about 11 million years. 11 million years that it would take the electron to be like, you know what? I'm tired of being in this higher energy configuration. And it's ever so slight, tiny, tiny. I still hate it. And so it's like, I'm not in any hurry here, but after on average 11 million years, it's like, okay, enough, and flips over. Of course, it's just the average, right? Like anything else in quantum, that's just the average. 11 million years. Okay, well, here's other things that can disturb an electron. Bumping into another hydrogen atom, bumping into anything else. In a laboratory, do you think it's on average 11 million years before a hydrogen atom would smack into another hydrogen atom and make gas of hydrogen in the laboratory? No, it would not be that long. And so because of that, you need a really, really low density gas for there to be any reasonable chance that a hydrogen will mind its own business long enough for an electron to make that transition. Can you think of a place where gas densities are really, really low? Like way lower than any vacuum we can make on Earth? Why, that would be in the interstellar medium. And so you can have clouds of atomic hydrogen in the interstellar medium, which give off this spectral line, this radio wave spectral line, 21 centimeter radiation. And so we can map it out next time, because we're done. Next time I'll point out the fact that, well, this is a very good wavelength for radio astronomers to use if they want to map out the distribution of hydrogen atomic gas clouds in the interstellar medium. Here's a spiral galaxy M83. Number 83 is listed on Charles Messier's list of things that are not comets. Here it is, mapped with radio telescope sensitive to 21 centimeter wavelength lines, and you can see from that that the interstellar atomic hydrogen is along the spiral arms of the galaxy. That's true in our galaxy as well. In fact, we use 21 centimeter radiation as one way to map out the spiral arms of our galaxy from within. And just to set you up to make you want to see that video next time, and SETI, Search for Extraterrestrial Intelligence, if you're thinking like, assuming that there's intelligence out there who would like to say hello, what might they use to talk to us? Well, if they infer that we have radio astronomers studying interstellar clouds, and therefore we would have specifically built telescopes to look for 21 centimeter radiation, why not deliberately broadcast a message at 21 centimeter wavelength? We humans have broadcast messages at 21 centimeter wavelength, saying, hey, anybody out there? Now, we, for example, broadcasted to the globular cluster M13, which is like 25,000 light years away. So that was back in 1974. We sent them a coded message if there's anybody listening. So 25,000 years plus 25,000 years, we basically said, hey, more sophisticated than that. Maybe in 50,000 years we'll get some, or something like that. Very long conversation. Anyway, you may know about, how many of you know what the WOW signal is? Right? The WOW signal, discovered at the Big Ear Radio Telescope, or detected at the Big Ear Radio Telescope on the grounds of Perkins Observatory, was an unusual amplitude signal at, you guessed it, 21 centimeters wavelength. And so here's Joe to tell us about the WOW signal next time. Yes?
Did you say this was discovered at the Perkins Observatory?
It was discovered at the Big Ear Radio Telescope, which was on the golf course that used to be part of the grounds of Perkins Observatory. So the Ohio State University Big Ear Radio Telescope saw the WOW signal. So it might be that first contact was made right here in Delaware, Ohio, which is why this is here. I'm not saying it's aliens, and I won't say the second part, but it is interesting to think, they're probably not, but we have an exclusive possibility that first contact was made. Right? Maybe they were going like, we always thought it was. Right? It's always jokes. It's like the one, help, 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 oh! Or something like that. If you've ever seen Monty Python in the Holy Grail, it's like when they're carving into the rooms and it says, oh, like, he wouldn't have carved, oh, etc. But maybe they were saying, oh, that's what I like to do. More next time with Joe, who has a very entertaining YouTube channel.